All right, well, we will get started for today. So this week we're working on chapter 8, as well as we're going to introduce chapter 9. So you will have homework coming up on Monday, and it will be regarding chapter 8 and chapter 9. When we discuss chapter 8, we're going to be thinking a lot about gases. So the last time that we were here, we made mention of Boyle's law, we made mention of Charles's law, and then we're going to add in a couple extra laws. We're going to talk about Gay-Lussac's law, and we're also going to mention the combined gas law. You will not be tested specifically on the ideal gas law, but I'm still going to make mention of it. So that way we can kind of end that little piece. And then chapter 9, we're going to start talking about solutions. So we're going to be discussing that if you mixed this particular substance in water, or you mixed it in some sort of alcohol, what would happen? And we're going to discuss concentrations and molar concentrations. So I think it will be fun. What I'm going to do is I'll do a little lecturing, and then we're going to do the breakout sections again. So I'll have some problems for you guys to work out in class. You'll get to work with a group, and then we'll go back over them as a group. So that way they make a little bit more sense and you get a little bit more practice in. So let's go ahead and go back to chapter 8 really quickly. So I just want to do a nice little review, make sure this all makes sense. So again, when we discuss the idea of gas laws, remember that when we think about a gas, it's part of that states of matter, so solid, liquid, and gas. And what they're saying is most of these atoms that are in the first two periods, and the noble gases as well, are going to be gases at room temperature. And so we see, for instance, again, molecular nitrogen, molecular hydrogen, molecular oxygen, and like our noble gases like helium, argon, those sorts of aspects here. Remember, when we think about a gas, they are going to try to fill their container. That's their ultimate goal. But they don't have very large volumes because, again, you have a handful of gas molecules, but their ultimate goal is they're filling their container. And what they do is they move very rapidly, and they move in these straight lines. And they essentially have no attractive or repulsive forces associated with them. But when we think about their energy, they have kinetic energy that will increase with temperature. So again, when we discuss the idea of gases, we talk about pressure, volume, temperature, and their quantity. When we discuss the unit for pressure, again, most often in chemistry aspects, we're going to talk about ATM, the atmospheric pressure, and we're going to be talking about millimeters of mercury, mmHg. Those ones are going to be units that we're going to discuss quite a bit. And we want to make sure that we can calculate back and forth with them as well. When we discuss volume, we're thinking about the space that's occupied by the gas. And usually we're going to see this in liters or milliliters. For temperature, we're thinking about that kinetic energy. And so again, it will increase with temperature increasing. So for calculation wise, we're going to be mostly mentioning things in Kelvin, but you can see them sometimes in degrees Celsius, and that's fine. And if we have to convert them to Kelvin, all we have to do is add 273. So if you had 35 degrees Celsius, you add 273 and you get your Kelvin. And then finally, when we think about the quantity of gas that's in its particular container, we usually will see it in grams or moles. But for calculation wise, we want to express it in moles. Why we don't show it as a little m always confuses me. I think it's because it has to do with molarity, which we're going to talk about in chapter 9. And I think just to make it different, they express it as a little n. Again, totally confusing to me why it's a little n, but just go with it. It's either going to be expressed in grams or it's going to be expressed in moles. And again, we can convert back and forth between grams and moles utilizing that molar mass. So when we see moles, we end up thinking about it as n. So we're going to be discussing this quite a bit more, and we're going to be doing some of these calculations back and forth, but I just wanted to kind of go back over that and give a nice little refresher. So when we think about the volume of the gas, again, we're going to be thinking about milliliters, or we're going to be thinking about liters. And what we're going to notice is when there's an increase in pressure, there will also, when there's an increase in temperature, there will also be an increase in volume, and vice versa. When there's an increase in volume, there's an increase in temperature. Now, vice versa, when there's an increase in volume, there's a drop in pressure. And when there's an increase in pressure, there's a drop in volume. So why we care about those is, again, it helps us with these gas laws. In terms of temperature, again, it's thinking about the average kinetic energy of those molecules. And we try to measure it using this Kelvin scale. So again, what you do is if you have your degrees Celsius, all you have to do is add 273. If they originally gave it to you in Fahrenheit, you would have to convert to Celsius and then add the 273. But what we notice is with gases, the temperature will decrease and there will be less collisions. Versus when there's an increase in temperature, they have more collisions. There's that increase of that average kinetic energy. So usually we're going to see this expressed in Celsius, or we're going to see expressed in Kelvin. And then, like I said, for pressure, we have quite a number of units. For the most part, we're going to be expressing units in mmHg. Like for instance, again, if you used a blood pressure cuff, a sphygmomanometer, you would calculate in millimeters of mercury. So 120/80 millimeters of mercury. But we can also use ATM, atmospheric pressure. And the funny thing is, millimeters of mercury is actually going to be the same number as torr. So it's kind of funny. If you had 760 millimeters of mercury, you have 760 torr. It's kind of a funny thing to do. So those will be the most common units that we're going to see for this guy here. And in order to monitor or measure pressure, we use a barometer. So again, when you think about your blood pressure cuff, it's actually kind of a fancy barometer to be able to measure and utilize those pressures. And we think about the pressure exerted by those gases. So again, one of the reasons that we do have torr is because of the inventor, this Torricelli, that actually came up with the barometer too. But like I said, for one ATM, it's 760 millimeters of mercury. It's also 760 torr. Don't ask me why, but it works very well for them. And again, we tend to think a lot in atmospheric pressure as well. So when we think about atmospheric pressure, we think about the pressure exerted by air from the top of the atmosphere to the surface of the earth. So we think about altitude in this aspect. And as altitude increases, your pressure actually drops. So again, this is one of the reasons that when you're in an airplane, they have a cabin pressure that's already sort of constant and stabilized, because the higher up you would go, you would actually lose that pressure, and it can cause detriment in your ears, and eventually you would pass out and faint and not do very well. So we don't want that to happen. Another big problem too is that those that live at higher altitudes also tend to have issues with gases, and they tend to have problems with respiratory distress because of that, or they've created such an accommodation for it that we may see some changes from a tissue perspective. Now, the conversion factors to know. And so what this is basically saying is how to equivalate 1 atmospheric pressure for all of these different units. So for 1 ATM, you have 760 millimeters of mercury. For 1 ATM, you have 760 torr. Those will be the only ones that really pop up. Otherwise, the other ones, you can definitely utilize this chart. They very rarely pop up. Like I said, the only reason I know pounds per square inch is because that's what my husband happens to work with in hydraulics. And some units will show Pascal, but very, very rare does that ever happen. All right, so we already did those little study checks, but I just kind of wanted to review. Now, this is where we ended off. We started talking about these different types of pressures and these different types of gas laws. And so the first law that we talked about was thinking about when temperature is constant, what happens to a gas with its volume and temperature. And we call this Boyle's law. So again, the way to remember this is that you bring to a boil. And really quickly, before we get going too far, what's going to end up happening is we're going to talk about what's called the combined gas law. And what it basically is showing is these changes and variations in pressure and in volume. Oh, I was gonna say, I apologize. Is the screen not moving with you guys? Sorry about that. We'll go, I was gonna say, I'll make sure it's moving. Let me see. Can you now see my screen now, the black screen? All right, perfect. All right, thank you. Sorry about that. See, I always need to know ahead of time because otherwise, if the screen doesn't move, I would have continued on and thought you guys could see what I was doing. So I'm glad that someone said something. Thank you. I appreciate it. All right, so we're going to first talk about the combined gas law. And so, like I said, the last time that we were here, we made mention of Boyle's law, we made mention of Charles' law, but it helps to know this combined gas law. And basically what it states is that your initial pressure times your initial volume over the initial temperature equals your final pressure times volume divided by temperature. So if you have this guy available, it will make understanding these laws just a little bit easier when we go to run through them. So for instance, when we discuss the idea of Boyle's law, again, think of boil, you bring to a boil. Temperature is constant. So what happens here is that you remove temperature. And so you'll say that P1 over V1 equals P2 over V2. And basically what happens here is you have an initial volume and initial pressure, and you're going to try to figure out the final pressure or volume. Or again, they could give you the final pressure and volume and the initial pressure, and they want to know what the initial volume was. But what will happen is there is an inverse relationship between these guys. So what will happen is as pressure goes down, volume goes up, and vice versa. When pressure is up, volume is down. So that's Boyle's law. And again, we'll practice this here in just a minute. Now we have another nice little piece to know. So again, writing out the combined gas law. Is we have Charles's law. And like I said, this, when I used to teach chemistry many moons ago, this was a lot more applicable. But I'd say that Prince Charles was under a lot of pressure. So pressure was constant, but basically know that pressure isn't changing. So we remove P1 and P2. And so what this is saying is that the first initial volume over the initial temperature equals the initial or the final volume over the final temperature. And so again, we can look for any of these variables as long as we know 3 of them, we can figure out the 4th. In this circumstance, when we're trying to depict these units, usually you go with what they start with originally. So again, if they gave you volume in milliliters, your V2 would be in milliliters. Unless they tell you otherwise, go with what the actual question is asking for. And so that's where we left off last time. So let's go ahead and do a little bit of practice with these guys to make sure that they make sense. So again, when we think about Boyle's law, we'll see this inverse relationship. The volume will go up, pressure goes down. Pressure goes up, volume goes down. And so again, we end up utilizing that combined gas law, P1 over V1 equals P2 over V2. We just remove the temperature. So let's go ahead and practice this problem again, just to make sure that this makes sense. A sample of oxygen has a volume of 12 liters at 600 millimeters of mercury. What is the new pressure when the volume changes to 36.0 liters at a constant temperature and N, which is the quantity, the moles that we're thinking about? And so because of the fact that it's telling us that we have constant temperature and constant moles or constant N, we know we're dealing with Boyle's law. So again, if you ever have that moment where you're not sure what law it is, use that combined gas law. In this circumstance, we don't have to care about these guys. We can remove that. And now that we know this, we know that we have 12.0 liters for our initial volume. And they tell us that P1 is 600 millimeters of mercury. Now, looking at this piece here, they give you 600 millimeters mercury. Why did they throw that dot at the end of 600? Does anyone know? Why would they do that dot? Was that just by accident or was there a reason for it?
Does it have to do with significant figures?
Yep, it's 3 significant figures. Perfect. So if you just did this and there was no decimal place, you would only have 1 significant figure. Very good. So when we think about significant figures, normal digits or straight integers are very easy. You count them all the time. But with zeros, you don't count leading zeros and you don't count trailing zeros that don't have a decimal place. So here they're telling you that you have 3 significant figures. Very good. And it makes sense. This guy has 3 significant figures because of that decimal place. And this guy has 3 significant figures. So I hope that makes a little bit more sense. All right, they also tell us now what is the new pressure. So this is what we're looking for. This is what we don't know, this new pressure, P2. When the volume changes to 36.0 liters. So now we're going to solve for P2. And so P2 will be P1 over V1 divided by V2. When we look at this problem and throw all the pieces together, we have 600 millimeters of mercury multiplied by 12.0 liters divided by 36.0 liters. What happens to our units here when we look at this little piece? What happens to the unit?
It triples.
So when we look at the liters down here and the liters here, they're going to cancel each other out. Very good. The liters are going to cancel each other out. So now all that you're left with is this millimeters of mercury. And it would make sense too that when you think about these numbers, because it went, because now the pressure or the volume changed and it went up by triple, you're going to see that this number is going to go down by that third. Very good. All right, so I'm not going to go ahead and calculate it. We already calculated this in class last week, but I wanted to go back through and make sure this made sense. Now, again, when we think about this, then we have Charles's law. And for Charles's law, we are going to think that pressure is constant. So again, when we think about that combined gas law, this makes life a little bit easier. Now you're worrying about V and T, volume and temperature. Now these guys are directly related. When temperature goes up, volume's up. When volume is down, temperature is down. They work together. So they're what we call directly related. So now when we go to monitor these guys, again, instead of using P1 V1 equals P2 V2, again, think about that ideal gas law, or I'm sorry, the combined gas law. And we remove pressure. And a lot of the times too, when you look at the questions, they will tell you what's constant. If you don't see them in there, you kind of assume they're constant, but most of the time they'll actually say like when pressure is constant, when N is constant. So you know you're only dealing with fluctuations between volume and temperature. Now here, it says the sample of a gas has a volume of 420 milliliters at a temperature of 18 degrees Celsius. Now, looking at this 420, how many significant figures do we have?
2.
2, very good. And then this has 2 significant figures. So your number at the end should have 2 significant figures. All right, now it says at what temperature, so now we're solving for temperature, will the volume of oxygen be at 640 milliliters? So now we're solving for T2. So like I said, there's a couple ways to do this, but you're attempting to isolate T2 on its own. So how I was taught to do this is that you multiply and cross multiply. So T2 times V1 equals V2 times T1. So these two multiply together, these two multiply together. And now I can isolate T2. And now when I go to look at my unit, just from looking at this example, this volume will be in milliliters. This volume will be in milliliters. Those will cancel out. And now all I'm left with is degrees Celsius. So like I said, we did this the one in class, but I just kind of wanted to run back through it and make sure these make sense. How do these gas laws feel? Boyle's law and Charles's law. Thumbs up if they're good. Questions if you have any at this point in time. Again, just wanted to do a little recap from last week. How are we feeling with that? Good. Perfect. I get to see a couple thumbs up, so that's good. Are there any questions? Good. Perfect. Okay. Now we're going to add on a new law. So this is called Gay-Lussac's law. And now what's going to happen is we're actually going to start thinking about, we're going to be thinking about temperature, we're going to be thinking about volume, and we're going to be thinking about pressure in this sort of piece. But what happens here is temperature and pressure go together and we stop worrying about volume. Volume is constant. So now when we look at that combined gas law, instead of worrying about temperature, it's P1 over T1 equals P2 over T2. And basically what this is saying is when the Kelvin temperature of a gas doubles at a constant volume and the amount of gas, so your N, the pressure also is going to double. So the pressure exerted by a gas is directly related. When pressure goes up, temperature goes up. When pressure goes down, temperature is going to go down. And volume, so ml, liter, and gas, which is our N, are going to be constant. So again, if we were to run this one here, you have, again, we'll just use the combined gas law. V1 over P1, T1, P2, V2, T2. It says a gas has a pressure of 645 torr at 128 degrees Celsius. What is the temperature in degrees Celsius if the pressure increases to 824 torr? V and N are constant. So right off the bat, we're not worried about volume. So we can get rid of that. Now we can go ahead and plug in our numbers. And remember, we're looking for temperature. We're looking for V or T2. So doing that little cross multiplying, P1 times T2 equals P2 times T1. I want to get temperature by itself. I want to get T2 alone. So I'm going to divide by P1 and I'm going to divide by P1 on this side. That cancels out. So go ahead and see if you can plug in the numbers. And if there's any questions, let me know. Oh, there was a great question. So does it matter if it's in torr or if it doesn't matter if it's in mmHg? So because they're both in torr, they're going to cancel out. But if they gave you one at 645 torr and one at 845 mmHg, you would have to do the conversion. So great question. But because this one, they're both at torr, they're going to cancel out anyway. So it's not going to matter. Great question. I'm glad that you asked. All right, so go ahead and plug those numbers in and see what you get. All right, what did you guys get for degrees Celsius? What did you guys get for T2?
I rounded up a little and I got 164 degrees Celsius.
Yep, very good. 164 degrees Celsius. Because if you got, I think it's 163.5, because it's three significant figures, you would round it up to 164. So to plug in these numbers, this would be P2, so that's 824 torr. Let me do red. This would be the 128 degrees Celsius, and this would be 645. Very good. And like I said, it comes out to be like 163.5 because it's three significant figures. We round it to 164. Very good. All right. Does this seem okay? Nothing too crazy here. I actually think these are fun. These are like you feel confident with these ones, and it's kind of a nice little pickup from the stoichiometry problems. I like these a lot more. Like I said, it's kind of funny because we put you through the stoichiometry and that's terrible and it's a lot of work. And then you get this, and you're like, okay, I got this. Plug and chug. You feel kind of good. So when it's easy, let them be easy. But like I said, it ends up totaling to this combined gas law. So again, when we think about this underwater, the pressure on the diver is actually greater than the pressure in the atmosphere. And so when we think about these pieces, we think about these gas laws and think about pressure and volume and temperature and how those relationships work together. So if you total up Boyle's law, Charles's law, Gay-Lussac's law, you end up with this combined gas law. And when we look at this, the quantity, the moles is constant. So we just say P1 times V1 over T1 equals P2 V2 over T2. I just like to know the combined gas law. And again, then you can just know what the constants are. Boil, bring to a boil, temperature's constant. Remove T1 and T2. Charles is under a lot of pressure. P1, P2, gone. Gay-Lussac's law, volume is gone. I think this makes it so much easier to be able to manipulate these equations. So as long as you kind of know the combined gas law, you can work your way through these problems pretty easily. And so again, this is just kind of nice to see the constants, the relationships, and again, the names of the law. Now, let's go ahead and do a little study check. So we got quite a few pieces thrown at us at this point in time. And if you start to kind of glance, we're going to notice that the units are all a little bit different. So we got to do some conversions before we actually start plugging and chugging these numbers in. So it says a sample of helium gas has a volume of 0.80 liters and a pressure of 0.800 atm at a temperature of 29 degrees Celsius. So P1, B1, T1, P2, V2, T2. This already kind of gave us some nice pieces. So now it says at what temperature in degrees Celsius, so we'll leave Celsius alone, will helium have a volume of 90 milliliters and a pressure of 3.2 atm. So before we even get started with plugging these numbers in, what do we have to do first? There's some conversions we got to do. So what would be the conversion we got to do? Look at some of those units.
Match the liters to the milliliters.
Very good. So you can do it either way. Because here they're going to cancel out, doesn't really matter. In my own mind, because there's something called the ideal gas law, which is PV equals nRT, volume should be in liters. So for my own thinking wise, I would convert it to liters. So how would we convert milliliters to liters? What would this end up being? Anyone know? What way would we have to move our decimal?
To the left.
Yep, we're going to move it left. So we're going to move it 3 places to the left because we want to get it in liters. So you move it 1, 2, 3. So this would be 0.09 liters because we had our little 0 here. 1, 2, 3. And if you guys are not super comfortable with conversions, stay after class. I'll show you a good way to do these. There's a simple way to remember how to do them. It's super easy. I always laugh because we teach chemistry so much harder. It's King Henry died unexpectedly drinking chocolate milk. So what you do is, this is your unit. So this is like your grams, liters, meters, kilo, hecta, deci, or deca, deci, centi, milli. Depending on what way you're trying to hit the unit, you're either going to move to the right or you're moving to the left. If you're going from milliliters, because this would be milliliters, to liters, you move 1, 2, 3 places to the left. If you were going from liters to milliliters, you'd move 1, 2, 3 places to the right. I don't know if anyone's ever seen those conversions, but it makes life a lot easier when you're going to do these pieces. Like I said, if anyone wants more practice with conversions, please let me know. I can definitely help you with those. And I do the cheating ways to remember them. So again, there's a proper way to do it with the scientific exponents, but otherwise just have to know what way you're moving it. But anyway, now we have our conversion. So what we're trying to do is we're trying to solve for what? It said, at what temperature in degrees Celsius will helium have on a volume of 0.90 liters and a pressure of 3.2 atm? So what are we solving for here? Are we solving for,
T2.
yep, very good. We're solving for T2. So to do this, I'm going to change my equation really quickly. It's going to be 2, P1, V1 over, equals P2, because we're going to cross multiply, V2, T1. I want to get T2 on its own, so I divide by P1, V1. That cancels out, divide by P1, V1. And now all you have to do is plug your numbers in. So go ahead and take a minute and try to plug in those numbers, and we'll see what you guys get. All right, did anyone get a number? Good, 58 degrees Celsius, perfect. And we'll stay at 2 significant figures because this 29 is at 2 significant figures. Very good. If it was 29.0, then we would take it out to be 58 point whatever it was. And I think it was actually just straight up 58. Yeah, nice and easy this time around. All right, hopefully these are making a little bit more sense. We're going to practice quite a few of them coming up here in just a moment, but at least it gives you a chance to sort of see how that practice happens. Now, why this starts to matter in healthcare and why it matters from an anatomy and physiology perspective is we start thinking about partial pressures. So there's a Dalton's law of partial pressure. And keep in mind, even when we think about the atmosphere, it's not all oxygen, it's not all nitrogen, it's not all carbon dioxide. Our cells are constantly moving gases through and back and forth. So when we think about it, especially for us, of what we're utilizing, we utilize oxygen and we blow off CO2. So both gases are moving in and out of the lungs, and they're going to be moving into these membranes, these tiny little sacs called alveoli. Alveoli are found in the lungs, and they're the site of gas exchange. And so what will happen is when we move through the cardiovascular system, when we go through the pulmonic circuit or the pulmonary circuit, we're dropping off CO2. We want to get rid of our CO2 and we want to pick up oxygen on that. And so that way we can utilize the oxygen through our systemic circulation. And so when we go to our tissues and our capillaries, we're dropping off oxygen to our tissues and we're picking up CO2. So because of this, we're going to have different distributions of carbon dioxide in certain areas, and we're going to have different distributions of oxygen. So in oxygenated blood, we have a pressure or partial pressure of oxygen that's about 100. Our partial pressure of carbon dioxide is about 40. And that should kind of make sense because we're going to be dropping off oxygen to our tissues. Deoxygenated blood, we actually have little oxygen, it's poorly oxygenated, and we have high volumes of CO2. Therefore, we can drop off the CO2 to the alveoli and we can pick up more oxygen. And also we have to think about the atmospheric pressure as well. And again, it's not just one pressure, it's multiple gases that are going to be combined into the circumstance. So when we look at the atmospheric pressure of oxygen, it's quite substantial. And it's low on the carbon dioxide aspect. So when we think about partial pressures, it's assuming that there's a gas mixture that would happen. And so when we think of the partial pressure of a gas, it's the pressure that each gas in this mixture would exert. So we can think about the partial pressure of helium at 2 atm. We can also look at the partial pressure of argon at 4 atm. And what you do is you just total them up. So you can find out the total pressure of these gases that are combined. Like I said, when we think about the atmosphere, we have molecular nitrogen, molecular hydrogen, molecular oxygen, CO2 in our atmosphere. So it's a mixture of all of these gases together. And that's what allows us to see these partial pressures. So when we utilize Dalton's law of partial pressure, it indicates that pressure depends on the total number of gas particles and not necessarily the types. The total pressure exerted by the gas in the mixture creates these sums of the partial pressure. So again, your P total is the mixture of partial pressure of oxygen, partial pressure of carbon dioxide, partial pressure of nitrogen that we would be thinking about. And that's what creates this law of partial pressures. So the total pressure, all of it, exerted by the gas in this mixture is the sum of all of your pressures totaled up. And so when we think about total pressure, so again, utilizing carbon dioxide, oxygen, and mixing them all together, we use this set point. It's called STP. And what it states is that at STP, this standard total pressure, 1 mole of a gas is going to have 22.4 liters for volume, and it will exert the same pressure as 1 mole of a gas with a mixture of 22.4 liters. Meaning, if you had a mole of nitrogen and you had 1 atm, it has that 22.4 liters. They all kind of work together. If you had 0.4 moles of O2 and 0.6 moles of helium, kind of in this combination that we see, again, it creates 1 mole and it creates this mixture at 22.4 liters. So you're looking at those total pressures and pulling them together. So we call this the standard total pressure, or STP. And so at STP, 1 mole of a gas in a volume of 22.4 liters exerts the same as your mixture. So again, your mixture of oxygen, your mixture of helium, your mixture of argon, all thrown into that mix. So when we hear the term STP, 1 mole, 22.4 liters, 1 ATM, we just kind of combine it all together. And what these mixtures aren't showing you here is that you're assuming that this volume, this container, is that 22.4 liters. But the 1 mole of O2 is the exact same as your combos. They all still have that same pressure. So when we think about the air that we breathe, it's kind of interesting. It's mostly nitrogen. It's like 70% nitrogen and I believe 21% oxygen. And the joke is that we actually only utilize like 17% of oxygen. So when we think about this and when we talk about atmospheric pressure, it's actually this sum, this partial pressure of all the gases that we think about in the air. So again, you think of nitrogen at 594, oxygen's at 160, carbon dioxide's at 0.3. You have water in terms of a gas that we think about. That totals up to make your 760 mmHg or your 1 ATM. So kind of a nice little nifty thing to think about and why that's important. All right, so let's think about partial pressure for a minute and kind of see where this will go with us. For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 ATM. If the oxygen has a partial pressure of 1280 mmHg, what is the partial pressure of helium? So now what we're going to try to do is we're going to kind of play a little backwards roll, if you will. So we know that we have this mixture of helium and oxygen. And what we said is that we have this partial helium and we have partial oxygen. And combined, they create 8.00 ATM. We know that the partial pressure of oxygen is 1280 millimeters of mercury. And now what we want to figure out is the partial pressure of helium. And again, temperature and volume are constant, so they didn't change here. We want to have it total up to this number here. So what's one thing that we can do? So we know what the pressure is of oxygen. We know the partial pressure of oxygen. We don't know the partial pressure of helium. But just looking at this little scenario, because all we have to do is total them up and we'll see that it comes out to this 8 ATM. What's the problem with the 1280 millimeters of mercury? Why is this not going to help us necessarily? Or what do we have to do to fix it, to make it useful, if you will? Because what we're doing here basically is we are going to look for this partial pressure of helium. So what we can do is do the partial pressure of helium equals 8 ATM minus the partial pressure of oxygen. But why can't we just do that right now and make it simple and quick and easy? What's the problem here? Why won't this work?
You have to convert to ATMs.
Very good. We have to convert to ATM. So knowing this, let's do our little conversion factor. How many millimeters of mercury are in 1 ATM? 1 ATM has how many millimeters of mercury? Look back on that.
760.
760, very good. So now we can use this as our little conversion factor. So which one's going to go on the top and which one's going to go on the bottom when we go to piece this together? What are we trying to get to? Do we want millimeters of mercury on the bottom or do we want millimeters of mercury on the top? If we're looking at this little piece here. What do we want to do? Yep, ATM will go on the top. Very
Bottom.
good. Yeah, millimeters of mercury on the bottom. Very good. So the millimeters of mercury cancel each other out. And now we can divide 1280 divided by 760. And what number do we get if we do that? 1280 divided by 760. I get 1.68. Very good. ATM. So now that tells us the partial pressure of oxygen. And so what it says is for a deep sea or to a deep dive, a scuba diver uses a mixture of helium and oxygen. So now what we're going to do is we're going to go solve for partial pressure of helium. And now all we have to do is subtract 8 from 1.68. And I get that it equals 6.32 ATM. Does this kind of make sense? How you're going to do these problems? Basically, partial pressures are knowing the sum. And so again, all we want to do is figure out the sum of these partial pressures. So they already gave us one, we just had to go solve for the other. Does that make sense? Any questions, concerns, or comments on that one? That kind of work its way through a little bit. Thumbs up if this makes sense. If you have questions about it, please ask. This is the time to ask for sure. Any questions? All right, we're going to practice this again coming up, but I want to make sure that this is coming together. Okay, so again, this is a huge deal when it comes to thinking about healthcare, because again, we think about this for our respiratory system and our cardiovascular system. These changes in gases are going to allow for us to either pick up CO2 or drop off CO2 or pick up oxygen. In the alveoli of the lung, we're picking up oxygen. We have less oxygen, so it wants to go from an area of high to an area of low. In the meantime, we drop off CO2, and then that way we can distribute it or get rid of it as our waste product. In the capillaries, while we're going through our systemic system, we actually want to get oxygen. We want it to enter our cells and release, and we want to get CO2 to pick up to be able to take it back to the respiratory system. So that's why in our tissues and when we're going through like our systemic circulation, we start off with oxygenated blood. And then finally, when it goes to that venular pathway, when we start to pick up the CO2 in our veins, that's when we start carrying deoxygenated blood. And again, then we go through our pulmonary circulation in order to pick up oxygenated blood, drop off CO2. In the systemic circuit, we drop off O2 and we pick up CO2. So we have this constant change back and forth because of these different partial pressures. So that's why it's so important to talk about. So in the body, oxygen flows into tissue because you have partial pressures of oxygen, and they're higher in the blood and they're lower in the tissues. They always want to go from an area of high to an area of low. So that's why we're able to pick it up. CO2 flows out of the tissues because the partial pressure of CO2 is higher in your tissues and it's lower in your blood. And again, this is what allows for that change and that exchange between the pulmonary circulation and the systemic circulation. So again, when we think about oxygenated blood, we have pretty high volume of that partial pressure of oxygen, and we don't have as much for carbon dioxide. For deoxygenated blood, we carry a little bit higher CO2 and a little less oxygen. So because of that, again, we care about what's happening in our blood and we care about what happens in the tissues. So depending on whether it's higher or lower, we'll have a drop off or we're going to have a pickup. In oxygen, again, for our tissues, we have higher oxygen in our blood, so it wants to move to the tissues. And when we think about CO2, because again, in our tissues, we have more than we do in our blood, we end up dropping it off and picking up CO2. So we drop off oxygen, we pick up CO2. a change of that will happen in the alveoli. So now again, when you're looking at deoxygenated blood, we don't really want that carbon dioxide anymore. We want to get rid of it. So we drop it off, and in return, we pick up oxygen. So we keep having these partial pressure changes back and forth, and that's what allows us to either pick up oxygen or drop off oxygen. And again, it has that transfer between our blood and our tissues. All right. So that is all I have for chapter 8. Let's go ahead and do a little bit of practice to make sure that that makes sense. So really quickly, let me go ahead and pull this up for you guys. Just one moment. I want to make sure I get this up for you guys. Sorry guys, just one moment. I thought I had it up, and of course I don't have it up. So I got to go back through. Okay, it didn't save. All right, sorry guys, one moment and I'll be able to get this to you. So weird. Okay, it like deleted what I need for you guys. Okay, we'll try this again. Hopefully this will work. Okay, so what I'm going to do is I'm going to send you guys over a Google Doc. You're only going to have to do 2 questions for the gas law, and then I'm going to give you guys a couple more problems to work on here momentarily, because like I said, this just didn't want to work. I don't know why it's not doing what I want it to do, but we'll figure it out. So the first couple problems that you're going to see are just for the gas laws. So there should be 2 questions for you guys to work on, and you guys are going to do them together in little breakout rooms. Where it says dilution, you're going to stop. So you only have to do up until the 2 gas laws. And then once it says dilution, that's going to be for chapter 9 that we're going to be practicing. So let me go ahead and break you guys into groups. You're going to see a Google Doc to open. And again, there will be 2 questions for the gas law for you guys to practice. So let me go ahead and get these breakout rooms together. And when you guys are ready, you guys can open it. So make sure you can pick up the Google Doc really quick. Make sure you have access to it. And then go ahead and go into that breakout room. I'll resend it as well. Okay. Problems. So it says, suppose you had 3.15 sample of neon gas at 21 degrees Celsius and a pressure of 0.951 atm. What would the volume be if the pressure increased to 1.92 atm while the temperature remained constant? So let's write out our little combined gas law. P1 V1 over T1 equals P2 V2 over T2. And what law is this that they told us? They didn't directly tell us, but what law is this? Boyle's law. So temperature is constant. So we just are automatically removing temperature. So now what it says is suppose you had a 3.15 sample of neon gas at 21 degrees Celsius and a pressure of 0.951 ATM. What would the volume be if the pressure increased to 1.9292 ATM? So what are we solving for here? What are we solving for? Are we solving for P1, T1? What are we doing here? What are we solving for?
V2.
Your V2, very good. So V2 equals P1, B1 over P2. And when you go to plug all those numbers in, what was your V2 that you guys got? What do we get? So this was 0.951. This was 3.15. This one's 1.292. What did you guys get when you solved for V2? Good, 2.32, perfect. And this should make sense because as your pressure went up, your volume went down. Boyle's law, they're inversely proportional. So we want to make sure that that makes sense. So this should be the answer total. Does that make sense? Yep, good. All right, perfect. Okie dokie. Let's move on to the next one. All right, a sample of nitrogen gas at 18 degrees Celsius and 760 mmHg has a volume of 3.92 milliliters. What is the volume of 0 degrees Celsius and 1 ATM of pressure? Nope, I got you, Leanne, you're good. So what actually happened here? This is a tricky question, but I like this one. So what's the constant here when we're looking at this piece? They don't directly say it, but what's our constant?
Pressure.
Pressure, very good. So 1 ATM is 760 millimeters of mercury. So we can just get rid of that. So now what we can do is it's saying, what is the volume at 0 degrees Celsius? We're looking for V2. So when we go to plug our numbers in, V2 times T2 equals V1 times V2. Divide by, oops, I think I messed this up. What did I do wrong? T1, there we go. That's why that didn't look right. I'm like, why does this not look right? So it should be T2 times V1 and then V1 times T1. Get my little eraser out here. T1. There you go. Divide by T1, that cancels out. Divide by T1. When we went to go do this number here, what did you guys get as your new volume? But wait, could we just do our new volume? What would happen if we just did our new volume and didn't make any changes? What do you think happened here? Another tricky question. So does anyone else see the dilemma here with 0 degrees Celsius?
Do we change it to Kelvin?
Change it to Kelvin, because otherwise you end up with a volume that's 0 too, and we don't want that. So you add 273. This now T2 becomes 273. But now we have to do the same thing to the 18. We have to add 273. And it's sad that I don't know this off the top of my head, but, or can do it in my head, 273 plus 18, 291 Kelvin. So this may change your number when you go to calculate it, but what did you guys get for V2? Because you can keep the 3.92 milliliters. That's not the problem. But we have to try to get that conversion to our temperature. So what was our new volume? What would be the new volume? Yep, 3.68 milliliters. Are these making sense, guys? Thumbs up if they make sense. If you guys have questions though, you guys are quite quiet, so I'm not really always sure. Shane's got a thumbs up. Are there any questions on these problems? Yeah, so you just rounded. So what will happen is when we round them, that probably was what ended up happening here. Like there was some rounding in the calculator, but you're relatively close. So yeah, it would be 3.7 if you rounded to the two, if you had two significant figures. Nope, that's not incorrect. You did fine. So technically, if we were going with 18 degrees Celsius, we would say that it was two significant figures. But I would just go into more detail. It just depends on the like on your homework wise for quiz wise, they would go off of they would go off the lowest significant figures. I went off the volume, the three significant figures, but no, it doesn't really matter. Yep. All right. Good job, guys. All right. Otherwise, everyone else, are these making sense? Questions, concerns, comments? Are you guys feeling okay? Are these a little bit better than stoichiometry? Yep, nope, that's okay. That's why we're practicing. That's why we practice. The more practice you get, the better these will be. And that's really the truth with chemistry. And it's not something you can just do one of and then you'll remember it. It's the repetition and the just practicing it over and over that is going to make you guys really good at this and make it a lot easier. All right, I added these two problems because I wanted to get you guys in a little extra work in. So let's go through it really quick. A sample of helium gas has a volume of 5.90 liters and a pressure of 825 millimeters of mercury and a temperature of 26 degrees Celsius. What is the pressure of the gas in ATM? So we automatically know we got to convert. When the volume and temperature of the gas samples are changed to 1460 mLs and 341 Kelvin, and the amount of gas is constant. So here we're using that combined gas law. P2, V2 over T2. Now here, when we start to do these conversions, what we're solving for here is we want to get P2. But what it's saying is that we have 5.90 liters for V1. We have 825 millimeters of mercury for P1. We automatically have to convert that because we want to get our number, we want to get our unit in ATM. So we're going to have to do some conversion here. So what I'm going to do is take the 825 millimeters of mercury. And what is that equivalent? 1 ATM equals how many millimeters of mercury? What's that equivalent, that conversion?
One ATM, 760.
Got it. 760 millimeters mercury. Perfect. All right. So now what we do is we utilize this, and what goes on the top and what goes on the bottom if we're trying to get rid of millimeters of mercury and we want to be an ATM. What would we have to do?
One ATM would go on top.
Yeah, and 760 on the bottom. Perfect. So now we've already gotten rid of that little conversion there. So we're good to go in ATM. So 825 divided by 760. We end up with, I'm going to go a little further out. I'm going to go to 3 significant figures. 1.09 ATM. All right. Then they told us that we have a temperature of 26 degrees. And I don't know why I keep doing this. It should be T1. Now, again, because we can see that our T2 is in Kelvin, what can we do to this Celsius to change that and get it converted to Kelvin? What's the quickest thing to do?
Add 273.
Yep, add 273. So we end up with 299 Kelvin. From there now, it's just manipulating our equation. So we now need to go solve for this P2. So like I said, I do cross multiplying. To me, I feel like that's the easiest. So you would have P1, V1, T2 equals P2, V2, T1. Divide by V2, T1, cancel out. Divide by V2, T1. So P2 equals P1, V1, T1 over V2, T1. And this should make sense now, because when you go to see your units in, our units will cancel out. Oh, actually, we have to do one more. We have to do one more little piece, because now our V2 is in 1460 mLs. So how do we convert this to liters? 1460 mLs. Are we moving 3 places to the left or 3 places to the right?
Left.
Left. So we'll end up with 1.460 liters. And like I said, if anyone wants to stay after and work on conversions, I'll show you an easy way to do this, because it's just so much simpler. So now you can go plug these numbers in. So now we know that our V1 is that 5.90. We know that we had 1.5 ATM. Our T1 was 299. And then we had our V2 now, which is the 1.460. And we had 341 K for our T2. If we go to plug these numbers in, what do we get for our P2? What do we get for our new pressure? What did someone end up getting when you total up all these numbers? Because now we should have P2 equals 1.50 ATM times R 590 liters times R 341 divided by 1.460 times 299 Kelvin. Yep, 5.02 ATM. Very good. All right, I hope these are making a little bit more sense. Like I said, you have this to practice with. So now you've got a couple more practice problems under your belt. And if you guys like these, I'll keep giving you guys practice problems to do in class. I think they help a little bit. All right, one last question to do, and then we'll go into chapter 9. This says in a gas mixture, the partial pressures are argon at 420 mmHg, neon at 95 mmHg, and nitrogen at 175 mmHg. What is the total pressure in atmosphere exerted by the gas mixture? So first of all we're doing is totaling up these partial pressures. So to start off with, all you gotta do is 420 plus 95 plus 175. And if we total that up, what did you guys get in millimeters of mercury? 20 plus 5 plus. So if you total all these guys up, what do you get? Anyone else?
690.
Yep, good, 690 mmHg. But what's the problem with the millimeters of mercury? What did they ask for?
ATM.
ATM.
So now we gotta take the 690 millimeters of mercury. And now we're gonna use our little conversion factor. 1 ATM equals 760 mmHg. So pulling that over here, what goes on the top and what goes on the bottom?
1 ATM on the top and 760 on the bottom.
You got it. Perfect. All right, so 760 cancels out, or the millimeters of mercury cancel out. So we have 690 divided by 760. And technically we would be at 2 significant figures if we were to do this because of the 95, and actually technically 420 because there's no decimal place is 2 significant figures. So I got 0.91 ATM. These ones are easy. Let these ones be easy. All you're totaling up is the number. So they give you the partial pressure, you're totaling them up. Or like the problem that we had as our critical thinking question in the lecture, we knew the total and then we were just figuring out one of the partial pressures. These ones are easy. Let these ones be easy. These are not the hard questions. So like I said, for this chapter, it's a nice little refresh from stoichiometry. If anyone wants additional practice problems, let me know. But I think that was a good little start. So hopefully you guys like doing a little extra practice. I think it's helpful, but you guys will have to let me know either way. How are you feeling with chapter 8? Thumbs up if you're getting it. Thumbs down if you don't. If you have any questions, just let me know. Cool. Perfect. All right, see a couple thumbs up, so that's good. All right, sweet. Like I said, much easier than stoichiometry. Yep, slowly but surely, and that's the thing, just keep practicing those ones. Nope, you're good. The thumbs up works. But yeah, it just will keep working on it. And like I said, if you guys want more problems, we can keep working through more problems as well. But all right, really quickly, let's go ahead and move on to chapter 9. And we'll have way more problems for you for this chapter. So next, what we're going to do is we're going to start talking about solutions. So when we discuss the idea of solutions, imagine, if you will, that we are taking some sort of substance and we're going to mix it with something else. So when we discuss the idea of a solution, like for instance, salt and water, this is a homogeneous mixture that involves at least 2 substances, but it can be more. So for instance, the formation of salt with water, we are going to total those together to make a mixture, or we call it a solution. And so when we discuss the idea of a solute and a solvent, a lot of times we think about water as being the solvent, but technically the solute is just the substance that's in lesser amounts. So you have 2 components. The solute is present in smaller amounts versus the solvent is present in greater amounts. More than likely, or usually in a biochemical perspective, water is going to be the solvent. It used to be, or like maybe like in other classes, we talk about the solute being what gets dissolved. The solvent does the dissolving. From a chemical perspective, we look by quantity. The smaller substance quantity is solute. The larger solvent substance quantity is the solvent. And when you mix them together, you end up with a solution, which is a homogeneous mixture. And so when we talk about solutes, they can be gases. They can be, is it not moving again? All right, can we see it now? All right, perfect. All right, can you see it now? The solutions. So here we have a nice little picture of the salt and water. So the solvent would be the larger quantity, the solute is going to be the lesser quantity. Dang it, eventually I will remember this. They changed my Zoom up, so now I have to actually hit another button to get the share to work. It drives me crazy. But I'm trying to make a conscious effort to remember, and clearly not. But anyway, so this solute can be a solid, a liquid, or a gas. And it spreads throughout the solution to where it's considered to be spread evenly. And the mix of solvents, because they want to make sure that they have the same pH to discuss them. And they're not going to be separated necessarily by filtration, but they can be separated by what's called evaporation. So when we discuss them, you can have them evaporate. So like, for instance, if you put salt in water and you heated up that water, you could have that water dissipate and just be left with salt mixture. And like I said, they're not visible, but they can give a color to the solution. So that's why we consider it to be a homogeneous mixture, because we can't really differentiate between the two. Now, water primarily is the most common solvent in nature. So we discuss water as a solvent quite frequently, especially when it comes to like biological systems. In the human body, we're made up of like 90% water, and water is mostly the solvent for all of our chemical reactions in our medium. Now, one cool thing about water is it's actually called a polar molecule, meaning that there are parts of it that have charges to them. Even though they're sharing a group of electrons, they don't actually share the electrons equally. So when we look at water, you have two hydrogens and you have an oxygen. This oxygen just has a greater pull for electrons. So because it wants the electrons closer to it, and electrons have a negative charge, this guy gets a slightly negative charge. And it leaves the hydrogens with a slightly positive charge. So because of this, they can form hydrogen bonds, and multiple oxygen atoms and molecules can come together. So we can see an additional bond here, an additional bond here, because this guy has partial charges. There's a partially negative charge on the oxygen, and there's a partially positive charge on the hydrogen. So because of that, they can form what are known as hydrogen bonds. And this is one of the reasons that water is actually a liquid at room temperature, although its molar mass is quite small and would normally be a gas. But because water acts as a solvent, it can actually break down some solutes and disassociate them into electrolytes. So we'll discuss that a little bit more just coming up. But when we form solutions, the solutions form when you have these solute-solvent interactions. And they're large enough to overcome the solute-to-solute interaction and the solvent-to-solvent interaction. This is going to make sense in a few minutes when we go to talk about this in more detail. But basically, there has to be a solute-solvent interaction, like salts and water. They have to interact with each other. And it has to be a large enough reaction, if you will, to overcome these other interactions. So when we discuss solutions, like dissolves like. So polar molecules are going to dissolve in other polar molecules. Non-polar molecules will dissolve in non-polar molecules. And they create these different combinations, if you will. So solutes that will form are, again, polar and polar. You'll have a polar solute and a polar solvent. They'll come together. Same thing if you had a non-polar solute and a non-polar solvent. They will come together. But they won't form if they're not like and like. That just doesn't happen. So this is a very important thing, again, from a biology perspective. If you think about like your phospholipid bilayer, that cell membrane, we talk about how it has those hydrophilic heads and the hydrophobic tails. And that's why certain things can't interact with the hydrophobic tails, because they don't work well together. And same thing when it comes to solutions, like when you have salt or have like a water and oil, the reason they don't dissolve each other is because they're not the same substance. One's polar and one's non-polar. And so like has to dissolve like. So when we discuss the idea of like sodium chloride is your table salt. And what will happen is when you expose it to water, that funny mixture of the hydrogens and the oxygen having those polar molecules, it's enough to overcome this bond between sodium and chloride. So sodium and chloride is an ionic bond. When you put them into water, they dissociate into a sodium ion and a chloride ion. We separate them. And the reason this happens is because water wins, basically. Water has this partially negative charge on it that gets it attracted to the sodium. And on the flip side, hydrogens have a partially positive charge, and that's what allows them to be attracted to the chloride ions. So because of that, we're able to actually start ionizing the salt crystal. It's able to undergo hydration because, again, the water molecules around on it pull it into the solution and separate them into ions. So that's why if you put pure salt in water, why it now becomes this salt water. It now ionizes into sodium ions and chloride ions. So the like dissolves the like. With a polar molecule or a polar molecular compound, they are soluble in water because, for instance, like methanol, this CH3OH, we call it methanol. Just as a heads up, if you were to drink methanol, a teaspoon of it will make you blind, a tablespoon will kill you. So we don't drink this. In case anyone was curious, ethanol is what we drink, but methanol is not. But anyway, we're going to talk more about that when we talk about organic compounds. But anyway, methanol is this polar molecular compound. And what happens is that we have this polar OH group. And that forms hydrogen bonds with water. So because of this, the polar solutes require polar solvents to form these solutions. And so that's what we can see down at the bottom. Originally, we start off with methanol. So we have our CH3 group, and then we have this hydroxide group coming off of it. You got your water as your solvent. So it's in larger quantity. This guy is in smaller quantity. So it's our solute. And when we put them together, you can actually see that this hydroxide group is basically forming, and again, it's going to be pulling these parts apart. So we're making now this water solution with hydrogen bonding that's occurring. So we make this methanol water solution. So again, likes have to dissolve likes. So really quickly, let's go ahead and do a check just to make sure we understand this idea of solute and solvent. Remember, solute is in lower quantity, solvent is in the higher quantity. So if we look at letter A, 2 grams of sugar in 100 milliliters of water, which one would be considered the solute and which one would be considered the solvent? Which one's the solute? So if we were to think about this, we have less of the sugar than we necessarily do of the water. So sugar would be the solute, and then the water would be the solvent. All right, let's try letter B. 60 milliliters of ethyl alcohol, which we're going to know as ethanol here coming up very soon. Ethanol is, for those that are over the age of 21, this is what we like. And we have 30 milliliters of methyl alcohol. Again, if you were to drink methanol, you would be in very bad shape. Which one is the solute?
Methanol.
Yeah, methanol, very good. All right. We have 55 milliliters of water and 1.5 grams of NaCl. Which one would be the solute in this situation?
NaCl.
NaCl. It's the one that we have in the lower quantity. Very good. And then when we think about air, we have 200 milliliters of oxygen and 800 milliliters of molecular nitrogen. Which one is the solute in this situation?
Oxygen.
Oxygen, very good. So the solute is always in the lower quantity. Very good. All right, now we have to think about what happens when you add these to water. So lithium chloride. When we add it to water, it dissolves. So if we were to look at this, what we would see is LiCl, H2O, you get Li plus Cl minus. And again, it would have a little AQ next to it to show the state that it was in this aqueous state. The Li ions, the lithium ions, are attracted to what? What happens with that water that makes these guys disassociate? So which one is it attracted to? The oxygen atom or the hydrogen atom?
Oxygen.
Oxygen, very good, because they have those positive negative charges that want to attract each other. And then what happens with the chloride ion? What happens with that chloride ion? What would this one be attracted to?
Hydrogen.
Hydrogen, very good. And oops, guys, just one moment. I think I hear my mom bringing over my son. Give me one moment and I'm gonna pause this real quick. Never mind, it was my dog. It's my dog jumping at the door. My son's coming too, so my mom's picked him up from school for me. But that's funny. It's my dog making a bunch of noise. All right, so very good. So again, like is going to dissolve like, and when you deal with water, it has to be strong enough to overcome this LiCl, this nice little compound, and disassociate it into ions. Very good. All right, so now when we start thinking about these solutions, remember that you're going to have a mixture of your solute and your solvent. And so the solute is in the lower amount, the solvent is going to be in the higher quantity. And this is what's going to allow us to have concentrations of these solutions. So sometimes you're going to hear about the fact that we have like a 12 molar concentration of hydrochloric acid. Sometimes we're going to talk about the fact that we have a 0.2 molar concentration. And what we're really looking at is we want to see how much is added. So we start off with some solute, and basically how much water did we add to make this specific concentration. The lower the number, the more dilute the concentration is. The grander the number, the more concentrated it is. So for instance, when I taught chemistry at Baker College of Flint, we had a back room where we did labs. And so we would keep stock solutions of all of our concentrations because it's too hard to keep a bunch of bottles of 0.2 molar concentration of NaOH. And then for something else, you need a 0.5 molar concentration. So what we did is we just had these really strong concentrated NaOH or strong concentrated hydrochloric acid. And what we could do is we could either add water to dilute it, or we could remove the water to try to make it more concentrated. So basically what ends up happening is, again, you have some sort of solute and you add it to water, and then it can make this solution. And again, the concentration can either be quite dilute or it can be very concentrated, depending on how much water is added. So in this situation here, what they did is they gave you 5 grams of Ki, potassium iodide, and they added it to this volumetric flask, and they added water to it. And it says they added the water to make the exact 1 liter of the Ki solution. So they added 250 milliliters. That was their goal, was to make this 250 milliliter solution, which is this 1 liter kind of piece, take place. They wanted to make a specific concentration. So you start with your solute and you're adding water to it to be able to make this specific concentration of solution. So how we look at this number is the concentration of the solution is expressed by the amount of solute over the amount of solution. And remember, when we think about the solution, it's the solute plus the solvent. Students like to just go with the solute over the solvent. Nope, you're looking at the solute, the smaller quantity, with the solvent and the solute added together at the bottom. So when we discuss these concentrations, this is going to be very useful for the next round of questions. We can either look at what's called mass percent, we can look at volume percent, we can look at the mass per volume percent, or we're going to look at what's called the molar concentration or the molarity. And when we discuss molarity, it's moles over liters when we start discussing this piece. But again, it's the amount of solute over the amount of solution possible. And remember, the solution is the solute and the solvent totaled together when we see this little piece. All right, so the first thing that we're going to try to calculate is mass percent. And so what this is just grams over grams, if you will. And then we multiply by 100%. The reason we multiply by 100% is because if we were just doing grams over grams, it would cancel each other out and we wouldn't have a unit. So if we multiply by 100%, we can call it the mass percent. And so what we look at here is the mass of the solute over that mass of the solution. And what we can figure out is that we have 100 grams of that solution for our conversion factor. The grams of the solute in 100 grams of the solution. And the reason that makes sense is because we can total it up to 100%. So it's a little conversion factor. And like I said, we're going to be utilizing this here in just a moment. So if we were trying to calculate mass percent of this KCl, this is potassium chloride in a solution, and it requires the grams of the solute in the grams of the solution. So we look at the grams of KCl, or we look at the grams of the solvent, and then we can just total up our number together. So what they did here is you found out, they told you that you had 8 grams of KCl, the potassium chloride, our solute, and then they told us that we had 42 grams of water. That's our solvent. So now we can calculate our mass percent. It would be the solvent or the solute over the solution. So the 8 grams is your solute divided by the 50 grams of KCl. And the reason that we get that is because we have the solvent plus the solute added together. And remember, because now we would have our units cancel out and we don't want that to take place, we multiply this number by 100%. So our mass percent would be 16%. So again, you're getting the mass of your solute over the mass of your solution times 100%. Does that kind of make sense as to what we're doing? And again, they have to give you the grams of the solute and they have to give you the grams of the solvent at least. You have to have one or the other. Doesn't matter which one, but you have to have one or the other. They can either give you the grams of the solution or they can give you the grams of the solvent and you can just total it up yourself. So let's do a practice problem really quickly. So let's do a practice problem really quick. I have one on my little cheat sheet here, I believe. Okay, so let's go ahead and practice with this one. Okay, if we're thinking about mass percent, and have we really talked about this yet? Yep. Okay, so we just want to know our mass percent for the solution. It tells us that a solution is prepared by dissolving 28.4 grams of glucose and 355 grams of water. So again, if we're looking for mass percent, it's the mass of the solute over the mass of the solution times 100%. Right now, we don't care about the final volume. That's not the big deal right at this moment in time. But if we were trying to calculate these numbers, what would go on the top and what would go on the bottom?
The 28.4 go on top.
Yep, so 28.4 grams will go on top. And then what goes on the bottom? Would it just be 355 grams of water? What would we have to add to this number?
28.4.
28.4, because it's the mass of the solution. Very good. And again, this number is also in grams. So if you do this, you will see you get 28.4 plus 355. It would be 28.4 divided by 383.4. So it's 28.4 divided by 383.4. And then we multiply by 100% to get our number. So if you multiply by 100%, what do you end up getting for your number? Anyone try it yet?
7.41%.
Yep, 7.41%. Perfect. So that's how you calculate those. Those are pretty straightforward and nothing too crazy going on there. Now, we also then have to calculate for what's called volume percent. So that was mass percent, and now we're going to calculate for volume percent. So put this together. Oops. I did not do this the right way. I wanted to. Okay. Play for this slide. Okay, there we go. All right, so now what we're going to do is we're going to calculate volume percent. So if you calculate volume percent, they're giving you the milliliters of the solute over the milliliters of the solution. For circumstances like this, again, you're going to assume that you have a certain amount of solute in 100 milliliters of solution as a conversion factor. Because again, the idea would be that it would total up to be 100%. But if they give you the volume of your solute and they give you the volume of your solvent, again, you can still calculate for the volume of the solution and then multiply it by 100%. But in some of these ideas, they can give you that you have to know that you have so much per 100 milliliters of the solution as your conversion factor. So sometimes you might need that as well. So they can either give you the numbers, or again, you can assume this little conversion factor here, that the volume of your solute in 100 milliliters of your solution. And then we can sometimes see mass over volume percent. So we give you grams of the solute over the milliliters of your solution multiplied by 100%. And again, same thing, the mass of your solute in 100 milliliters of the solution would be your conversion factor. So that way we can total this up to be that 100% sort of piece. So that way we can figure this one out. But again, most of the time they're going to give you the grams, and most of the time they'll give you the milliliters. But in case they don't, again, we can always assume that we have these mass of our solute in grams in a 100 milliliter solution. So the solute plus the solvent. Okay, so really quickly, they are going to give us here our molarity. And really quickly, they didn't talk about this yet, but let me go ahead and try to explain what's going on here. Oh, wait a minute. Hold up. Did they not give you molarity? I didn't look at this slide. Okay, so one thing that we also are going to make mention of, because they didn't make mention of it, so we're going to do a little additional slide here. So if you have your notes, go ahead and go through this. Sometimes we're going to talk about the molar concentration. And the molar concentration is also known as molarity. And we represent molarity as big M. And the molarity is your grams per milliliter, or your grams per liter that we're dealing with. So when we discuss the molar concentration, they mentioned it here just a minute ago, didn't they? They put it down here. It's the moles of your solute over your liters of solution. And so when we discuss the molar concentration, they're going to give you M. We can use this as a conversion factor, just as we did with like molar mass and how we talked about molar mass as being grams per mole. We can do the same thing here with molarity. We can talk about the moles of a solute over the liters of our solution. And we can use this as a conversion factor. So moles of the solute over liters of our solution. And so that's what they're going to have us do here. Sorry about that. I thought we had 2 additional slides. I may have accidentally cut them out. I don't know what I did, but there should be more slides for molarity and molar concentration. So what this is going to ask us to do is figure out how many grams of aluminum chloride are needed to prepare 125 ml from this 0.150 molar stock solution. And remember, molarity is your moles over liters. It's your moles of your solute over liters of your solution. So what they do here, and again, the way I like to sort of write these out is what you know and what you don't know. So we know that we have 125 milliliters of our solution. Really quickly, because we're going to do some conversion, let's get this into liters. So how would I convert 125 milliliters into liters? How would I do that? How would I convert?
Move the decimal left 3.
Yep, move the decimal left 3. So a little bit 1, 2, 3. 0.125 liters. Perfect. We also know, sorry. Okay, no problem. That's my mom. Hi, everyone. This is what happens when you work from home. Anyway, I also have the molarity, which is 0.150 moles over liters. And for right now, let's go ahead and keep thinking of this moles of the solute over liters of the solution. In this circumstance, this AlCl3 is our solute. And what we don't know is we want to have grams of AlCl3, and we don't know how to get there. Okay, so we were given quite a bit. We have to make a plan really quickly. So the first thing that I would do is I would start with the 125 milliliters, and that we converted it to liters. So what I would do is I would do liters multiplied by my molarity. And the reason that I would do that is because then I would cancel out my liters. And what it would do is it would leave me with my moles of the solute. Now, here's the thing. I don't want to be left with my moles of the solute. I want to get to grams of my solute. Now, although it's been a brief minute, how do you go from moles to grams? So how do we go from grams to moles and moles to grams? What's one piece that we can utilize to make that happen? How do you convert from moles to grams and grams to moles? What do we use?
Molar mass?
Molar mass, very good. We can use the molar mass. So we're going to make a little plan. Always start with what they give us first. So we'll start with this 125 milliliters. Again, we already converted it to liters, and we'll multiply it by this molarity. So that way we can get rid of this number here. That will take us to moles. That'll give us our moles. And then from there, because it asked for grams, we're going to then go and get our molar mass. And from there, we're going to divide by our molar mass. So let's go ahead and clear this really quickly so that we have a little bit of an idea. So we're going to start with 0.125 liters and multiply it by 0.150 moles over liters. That's our molarity. Liters cancel out, and now I have moles of AlCl3. And now what I can do is I can multiply by the molar mass in order to get to grams. So I need to know how many grams of AlCl3 I have over 1 mole. And how would I find out our molar mass? How do we remember how to get molar mass? What do we have to use?
The periodic table.
Periodic table, very good. So the molar mass, AlCl3, it's about 133.3. We'll go with that for right now. Kind of somewhere in that range. So now our moles cancel out. So we went from our volume and we went and got our moles. And now we can go and get grams. So that's a little bit of our goal of how we're going to go ahead and get these. So if we total this up and got 0.125 times 0.150 multiplied by 0.133, what number do we get? What would be our final number here? What would we get here?
2.5.
Yep, good. And we'll stick with 3 significant figures just because that's what we have here. So 2.50 grams. All right, let's go ahead and practice one of these because these are a little bit confusing. So let's do a little bit more work with this one. All right, new share. Let's go back to this piece here. All right, this is a molarity question. And it's kind of mixing those pieces together. So it's mixing mass percent and it's going to mix molarity in the piece. So it says an aqueous solution is 8.50 ammonium chloride by mass. So if you did the mass percent, the mass of the solute over the mass of solution, you get 8.50%. It tells you the density of the solution is 1.024 grams per ml. We want to figure out what the molarity is in the solution. Now remember, molarity, why isn't this open up? Okay. Molarity is your moles over liters. It's the moles of your solute over the liters of your solution. Now you may look at this and be like, wow, this had a lot of pieces to it. And it seems kind of confusing how it's mixed together. But what it's actually going to do is it's going to give us a couple pieces that we need. It's going to help us to find our moles and it's going to help us to find our grams. So when we go to look at this piece here, let's first start with this sort of density portion to it. It's going to give us that we have 1.024 grams of our solution times 1 mole. I'm sorry. Actually, let's skip this one just for right now because we haven't talked about the mass percent. I want to give you guys another mass percent with molarity. Let's put a pin in this one and I'll come back to it and we'll do another practice problem really quickly because I want to make sure this makes sense before we do another problem. So put a pin in that one. I will bring it back. All right. So let's go back a little bit just to make sure that this is making sense and gets a little bit of a clearer piece. When you talk about the mass percent, again, we talked about how it was the grams of the solute over the grams of the solution. And like I said before, when we look at this piece, like hypothetically, that told us that we had 8.5% for our mass percent. what that is saying in a nutshell is that we have 8.5 grams of solute over 100 grams of our solution. So I want to put a little pin in that for right now, and then we'll come back to that problem. Does that make sense of what it's saying? So that way we can kind of figure this out. Because again, we're assuming that we had 100 grams of our solution to equivalent out that 8.50%. What it's saying is that, again, we have this many grams over of solute of our salt over 100 grams of our solution. And that's how we can calculate the mass percent. Again, sometimes we're going to get the volume percent where they give us the milliliters over the milliliters. And again, same thing, we can assume that if we had 8.5% our volume percent, it would mean that we had 8.5 milliliters over 100 milliliters of our solution. So we can utilize that in that piece here. And then, like I said, we can get to know our molarity. And our molarity is going to be the moles over the liters. Now, sometimes when we talk about mass and volume, we can have the grams of the solute over the milliliters of the solution. And again, same thing, we can utilize that. The grams of our solute were over 100 milliliters of our solution to figure this one out. So that's going to kind of bring us back to that next little piece that we're going to do. So let me pull this one back up so this can make some sense when we go to talk about these pieces. Okay, so this one says we have an aqueous solution of 8.50% ammonium chloride NH4Cl by mass. So what that is telling us is that we have 8.50 grams of our solute over 100 grams or 100 milliliters of our solution that we're talking about. That's what that mass percent is basically giving us. We also are given the density. And when something is discussed with density, we're going to be thinking about it in terms of grams per ml. So it's telling us the density of the solution. Hold up one second. Sorry, otherwise my son will be super loud. They'll say the density is going to be 1.24 grams of the solute over, again, when we think about that, whatever our solute or milliliters are of our solution. And what it wants us to find is the molarity of NH4Cl. And our molarity will be found as the grams of our solute over the milliliters or the liters of our solution. So we can use both of these pieces to our advantage, basically, to try to figure out these numbers. So remember, this is the solute. This is the solution. We want to get rid of the solutions, the grams of the solutions on the bottom, and we just want to figure out what our solute is. We want to figure out what the grams of our solute is and convert it to moles over the liters of our solution to try to have this make a little bit more sense. I think I'm confused. Am I confusing you guys more? Is this kind of making sense?
I'm confused.
Okay, let me give you guys a different problem because I feel like I'm confusing you guys. Like, I'm like, this is not what I'm wanting to do. All right, let's try another approach and I can give you a better example and then we'll come back to this one because I want to make sure that I'm explaining it in a way that makes sense. So thank you for letting me know either way. All right, let's go here. Let me pull out a practice problem from your guys's homework that we can go through really quickly and have it make sense. Actually, we'll go through a couple. So really quickly, I'm gonna pull out a homework problem for you guys to do. So that way this can make a little bit more sense. And then we'll go ahead and do dilutions. And dilutions are actually the easier part. So at least that one will not be so difficult to run through, and it'll be a little bit easier to explain. Molarity is hard to explain, and so is mass percent. So I'm always like, I'm hoping I'm explaining it, but I'm trying not to confuse the living daylights out of you guys as I'm saying it. Okay, so let me practice with this one. Let me give you a practice problem. Let me see. Why can I not find one that I want to show you guys? Sorry, guys. I don't know why this is taking me so long to find a problem. It's driving me crazy, actually, running through these. Let's see. Nope. I'm trying to find you guys a good practice problem to do, and I cannot find one for the life of me. Okay. Okay, here's one that we can do. All right, this one just wants us to calculate. This is a good starting question. And then, like I said, we'll do a little bit more problems. I'll find you guys more problems to do, and I'll work through them so that way you guys get to see them, so that way we don't run out of time. All right, it says calculate the mass volume percent for the solute in each of the following solutions. So for this one here, when we're running through it, I'm like, sorry, it took me forever to find a problem. It was driving me crazy. It says that we have 60 grams of the sodium sulfate in 300 milliliters of a solution. So if we were to calculate the mass per volume for this, it would be 60 grams of your Na2SO4. That's our mass of our solute over the 300 milliliters of our solution. Because when we go to do this problem, what it's asking for is the mass per volume. And so the mass would be in grams over the volume. And we're going to times it by 100% to get our mass percent. So if we were to do this, you do 60 divided by 300, you would get 0.2, and we multiply by 100 to get 20%. If you're doing mass percent, you do the mass of the solute over the mass of the solution. Do those make sense? Any questions, concerns, or comments on that one? Does that one make sense? Yes, no, maybe.
Yes.
Okay, perfect. All right, so then when we do molarity and we're calculating the molar concentration, what you're doing is you're saying that molarity is the moles of your solute over the liters of the solution. So they could give you the grams of the solute, they could give you milliliters of the solution. And what you're trying to do is you're trying to manipulate the equation. So sometimes you'll see it to where they'll ask you to find moles from liters. Sometimes you're going to be asked to solve for grams. Sometimes you're going to be asked to solve the molarity. Like I said, for some reason, I cannot find practice problems for those questions, but I promise you I will get you some. And what I'll do is I'll just make a little additional video for you guys to watch so you can run through some of the practice problems. From the looks of it, it doesn't look like there's many of them found in this chapter. So I'm kind of a little bit like, where the heck are they? They should be in here, but alas, they're not showing up. So it's kind of making me a little worried, but all right, we'll go ahead and we'll practice that again coming up soon. All right, next thing that we're gonna do. So like I said, just no mass percent and no volume percent and then molarity, just standard what they are for this moment in time. All right, the next thing that we're going to do is we're going to discuss the idea of dilutions. So like I said, when we discuss the idea of molar concentration, it could be 12 molar concentration. So it's 12 moles of your solute over the liters of the solution. It could be 0.25 molarity or molar concentration. And so what happens here is when we discuss the idea of dilutions, you're adding water to it. So you're making it less concentrated and you're making it more dilute. So here what you're going to see is that we use a can of orange juice. We're going to add water to it. And then when you mix it together, you're going to end up with this different type of solution. It's not going to be as heavily concentrated necessarily, but you'll end up with this dilution of your concentration. Now, if we add more orange juice, like so for instance, if we added 3 cans of orange juice, it can make it more concentrated. But if we added more water, it's going to make it more dilute. And so again, when we think about solutions, again, a dilute solution has less solute for a greater volume of water. A concentrated solution has more solute and a little less volume of water. So more concentrated, more solute we have present. More dilute, the more water has been added, the more of that solvent has been added. So in a dilution, water is added. When the water is added, obviously your volume increases because you're adding more water to it. But your concentration level is decreasing. So it's making it less concentrated. But the mass of your solute never changed. So again, we started with 3 grams of sodium chloride. If I add 1 milliliter of water, the mass didn't change if I added 6 milliliters of water. The mass will stay the same. It's the volume that ends up changing. But because of the fact that I changed the volume, it's going to end up changing my molar concentration. So when we discuss this, we utilize it as M1V1 equals M2V2, or we say it's a concentration. I prefer to remember it this way, but you guys can choose what you like. They talk about it as the concentration, but we discuss it as the molar concentration. So we say M1V1 equals M2V2. The molarity of the initial and the volume. And then what's going to happen is you're adding water here. So because you're adding water, your volume is going to go up for V2, as well as your molar concentration is going to change. But instead of it being more concentrated, it's going to end up being more dilute. So let's give a little practice problem. So this one, they gave us a concentration. It gave us a volume of 2% moles by volume of hydrochloric acid solution. And it's prepared by diluting 25.0 milliliters of this 14% HCl solution. What this number is giving us is the moles per volume that we're looking at here in this percentage wise. We don't want to look at it necessarily as percentage. We want to be able to look at it as a normally as a molar concentration. But so what we're going to do really quickly is we're just going to pull this out of a percentage, make our lives a little bit easier when we're going to look at this piece. So let's just call this our concentration. It's 2%. What we're going to do, because what this is saying is that we have basically 2.00 moles of our solution over 100 milliliters, or our volume of our solution. So what we're going to do is we're just going to divide by 100 to get our number. This gives us 0.002 of our solution that we're looking at, of this molar concentration or of our concentration. And same thing for that 14%. Again, we're going to divide that by 100. So that'll give us 0.14 of this molar concentration that we're looking at. And so what it did is it gave us M1 and M2. It says the volume of this can be prepared. So this would be our M2. By diluting 25 milliliters, so that would be our V1 of 14.00 hydrochloric acid solution. So that would be our M2. And what we want to do is we want to know what our new volume is going to be. So we have M1 V1 equals M2 V2. And again, when you read this, it's read a little bit funny. I always think that these are funny, like the way that we read them. We say that the volume, again, our volume is going to be prepared by diluting. So this is our V2. We're going to solve for V2. So what's our new volume that can be prepared when you dilute 25 milliliters of this 14% hydrochloric acid solution? So this would be our V1, this would be our M2, and that 2%, I'm sorry, that 14% would be our M1, and this guy would be our M2. So we're solving for V2. So remember, M1 V1 equals M2 V2. We want to know what V2 is. So we're going to divide by M2. This cancels out. We're going to divide by M2. And so what happens is that your V2, we don't know. Your M2 is at 0.02% or moles by volume. We have our V1, which is this 25.0 ml. And we have our M1, which is 0.140 m, kind of like that. So now we can go plug our numbers in. So when we go to plug these numbers in, V2 equals 0.140 m multiplied by 25.0 liters. And we're going to divide it all over 0.02 m. The molar concentrations go away. And now what we're left with is liters. So what's going to happen here is we're going to notice that our number is going to increase. Our V2 should go up because we are adding more water. Because if you notice, we started with this 14% hydrochloric acid solution originally, and now we diluted it to 2%. So in order to make that happen, we had to add more water. So we basically took this molar concentration of 14. Again, you multiply it by 25 milliliters, because that's what we started with originally. And then we are going to divide by our new molar concentration. When we get V2, what happens is you have 0.14 times 25, and we divide by 0.02. What is the new V2 when you total up these numbers?
175.
175. And that's in milliliters. So what that's saying is you had to add 150 milliliters of water to go from this 14% to 2% of this concentration to make it less concentrated and make it more dilute. Now, I know that we ran out of time, so I do want to practice these more with you guys. So what I'm going to do is, it probably won't be tonight, but it'll be tomorrow. I'll post an additional video doing some practice problems with you guys in order to make sure this makes sense. So keep on the lookout. For some reason, Canvas is not letting me post the videos anymore, so I have to just add it to the Google Drive. but I'll add it to the Google Drive along with the practice problems for you guys to do at home, because otherwise I know we ran out of time. Sorry for a little bit of confusion there at the last little bit, but we'll go back through it and I'll give you some more practice problems so you guys can go ahead and work through this. If anyone has any questions, feel free to stay on. If not, I will see you guys next Wednesday. So like I said, be on the lookout. I'll have more practice problems because I don't want to leave you guys just doing one problem. I'll have more practice for you. So just kind of keep your eyes out for that Google Drive video.